哎，对，以前的衣袍你身上去，
看出来，在我的衣袍你身上哦，他的衣服，如果有面包的话，可以的话，哇，这可以，有爱啊，没加深，加深，搞惯了面包。
你讲这么你没有面包不是？因为你要会蒸，你不要面包。
多少？有人觉得现在自己开始优过了，
所以有刚性。
没有啊，你写了很久啊，这句话写了很久。
哎，方天，你讲哪里？这个啊，这个很奇怪，这个为什么很奇怪？你要把这个 orange 呢全部想成是一起的啊，然后它这边是一个 plan 来的啊，就是画一个这个三角形的啊，想找 phi 跟 theta 哈，没有，你这个要把它想成这个东西先，你才会懂。它是那个 sphere 切成四半，然后它再切这边5度，懂吗？不是空是这个东西，你看空是这个，这个哪里是空？那个空那天那时候讲空是空的这一 side slender height，没有，你看它它这边切的时候啊，是一个 can 吗？presentation 啊，给我想一下，嗯，morning 眼睛呢？眼睛呢？哦，做 present 不可以戴眼镜啊？什么啊？我们应该讲话，我们想看到是 spherical 啊，然后哦，这样你要看它的 spherical 要给3个 那个吗？variable 吗？这样你要先看它 radius 多大哦，知道啊？因为它上面是 bound by 这个圈啊，这个 sphere 啊，这个 sphere 啊，你看上面这个 part 是 bound by 这个 sphere 啊，下面这个 part bound by 这个东西哦，但是这个东西在 spherical 里面有意思哦，这个下面这个 square root 啊，加圆圈，圆圈，square 圆圈，这个你看这个是一个 啊，对对对对，没有错。但是我是说，这一条线，这条直线是一个从 Z 下来的一条线嘛，这边就是那个 phi 哦，对吗？And then phi 有了过后，有 radius 了过后，然后你就要转那个 theta 哦。等一下，
等下没有聊过。那里面有地瓜。
啊，
早啊，多啊，
通常什么？不是什么？
都是2排。
没有啊，那是你最大可以拿的号码，
有人拿。
多不可以？你一粒吃得完没？你看放冰柜先吗？你吃不完可以放冰柜先的吗？最好放冰柜吗？等一下，
这个我看到都是同一
哎，你不是也不知道，但是这个打开 angle，我是在找 x 跟 y 的那个 plane 的那个 angle。
啊
这是泡面的。
，from positive x-axis 啊，这么有泡面的哦。等一下，
很少。
等一下，
那你很低调啊，不想吃啊。
我现在还是有点醒，刚醒。
钢琴。
是啊，全部跑去做 presentation。
presentation。哦，我放开啊，连眼镜翻过来，没有放到我这样看，然后我电脑奇怪的这个这样。
Testing 啊，Let's start 打了。
不要再说。
Let's okay. Okay, so let's recall what's curl last time. What's curl? Not last time, yesterday. Curl is the cross product between what? Gradient operator and vector field. Okay, gradient operator and vector field. Okay, and then so you will get these three terms here. Okay, actually, last time we said that if curl is not zero, then f is conservative, right? Okay, so if curl is zero, is f conservative or not?
Yes.
Actually, yes. Why? Not if and only if. The statement, original statement is not if and only if. But last time we have this. Yeah. So last time we have this criteria, right? This is an if and only if criteria, right? So if we want to check f is conservative, then we need to check this three equality here. So today, I tell you where this three equality come from. These three equalities here are coming from the curve. Can you realize or not? You see, del f1 over del y minus del f2 over del x. What is this curve here? Okay, let me bring the curve down. Okay, so can you see? If I set the curve to be 0, okay, the first thing here, del f3 del y minus del f2 del z equals 0. Then you will get the which equality? You will get the herd equality. Okay or not? Can see or not? Hello, hello. Okay, so let me write set of f equals 0. Okay, what does this mean? Okay, this means that every coordinate is 0. Okay, every coordinate is 0. Correct? Okay. Can you see that if I set all the coordinates 0, I get the exactly 3 equation here? Can remember or not? Can see or not? How to see? Okay, so if I set curl equals 0, what is curl? Then, wait, okay, so if I set my curl to be 0, my curl have 3 terms, right? So I set my vector equals 0. Okay, if I set my vector equals 0, every terms here need to be 0. Okay, so if first one becomes 0, mean what? Partial derivative of f3 with respect to y minus partial derivative of f2 with respect to z is equal. Right? So this is the third equality here. Okay, and then second to be 0, del f1 del z minus del fx del x equal to 0. Okay, which is the second one. Okay, the second one. Okay, if you set the last one to be 0, then you get the first equality. Okay, so now I tell you where this 3 equation come from. Okay, they actually can be obtained from the curve. Okay, setting the curve to be 0. Okay, so you don't need to memorize, no need to by heart this. Okay, you just need to make sure you know how to compute the curve and then set the curve to be 0. Yeah, cross product. Yes, yes. Okay, of course there's some other condition, right? So you need to work on this simply connected open domain and also f1, f2, f3. The partial derivative is continuous. Okay, these 2 extra condition you just need to check. Okay or not? So this meaning what? Meaning this condition here is to set curl of f equal to 0. Okay. Okay. Okay, so if you try the review question, right? Okay. So if you try a review question, you will see this question here. Okay. I want to like this one. This one is the multiple integral. No, I just want to like because no, because someone asked about it, right? So I want to like address this. Yeah, Qingrou asked about this how to plot this graph, right? How to plot this domain here. Oh, I haven't started. I just want to recall. Just now Qingrou not here, so I delay this part. I want to address this in the class. I want to post this as well. I scared you later don't know what I'm doing. Okay. So I want to so there's a review question involving this domain here. And this domain kind of hard to imagine. Okay. So kind of hard to imagine how to do this kind of question, right? So we know that the inner variable is controlled by the outermost variable, right? Outer variable. So you start listing out the range of the variable from outer to inner. Okay. Okay or no? Okay. And then how do you draw the domain? Okay. The first step is you start with the outermost domain. Okay. Outermost domain usually start with constant. Okay. So you can draw if x is between 0 and 1, how do you draw it? It's just a line. Okay. But if you go to the second step here, okay, you involve x and y already. So you have x and y, 2 variable. You have 2-dimensional picture. Okay. So you have 2-dimensional picture. y is controlled bounded below by 0, bounded above by the square root 1 minus x squared. What is 1 square root 1 minus x squared? Semicircle, right? Okay. But to draw a full semicircle, you need to go from -1 to 1. But now your x is only going from 0 to 1. So it's a half of the semicircle. Okay, so I draw a half of the semicircle. Okay. And then how about z? Okay, z is the hardest one here. Okay. Z is controlled both by xy and both xy, right? So meaning if you have this 2D shape, right, you need to add an extra z here, correct or not? Okay, so over every xy, right, you have different z. Okay, so how to do? What to do here? What you can do is you look at slice by slice. Okay, my slice here mean the zx plane, zx plane. So you need to imagine you got a 3D, right? You got a 3D picture. You look at one plane first. Okay, y equals to 0. How does the plane look like? Y equals to 1, how does the plane look like? Y equals to 0.5, how does the plane look like? Okay, then you combine this plane, right? So you see it like a movie, right? A movie. So how does the movie change? Right? So you see, in the third picture here, I see this movie here. I start with this, how do you call this? Let's call this a pizza. Okay. I start to see how this pizza change when y vary. Okay, you can see that this pizza getting smaller and smaller and smaller until you get a point. Okay. So if I put this together here, I will get a portion of the sphere. Okay, I get a portion of the sphere. You can try and have a look and then tell me what do you think on Thursday, yeah, last day. Yeah. Okay. Yeah, so I mean, in general, right? In general, this is how you draw this picture. Remember how I tell you how to make a line. You need many dots. Okay, how to make a surface? You need many lines. How to make a solid? You need many surface. Okay. Okay. So you can see that I want to make this line. I got a lot of dots. Okay, infinitely many dots putting together. I got a line. How to make this surface? I got a lot of line, infinitely many line to make out the surface. Okay. How to make out this solid here? I got infinitely many surface put together. I make out the solid. Okay. Try and read the slide again. See what do you think, and then compare with the working in the review exercise. Yeah, I mean this one is the, I would say, hard question. Okay, this will be hard. Okay, okay. If you don't understand what I say, right, so please ask. Okay, okay. If no question, we return to yesterday topic. So let's recall what we did yesterday, right? Okay. Just now we recall curve, and then what we also define is the surface integral. Okay, surface integral. In surface integral, what do you need to do? So how do you think of surface integral? Really, you should think of it as a generalization of line integral. Okay. If you want to do line integral, you need to parameterize your line. Okay. So in surface integral, you also need to parameterize your surface. Okay. Okay. So let's see this question here. So I want to evaluate the surface integral where x is what? There are three sides of x, x1, x2, and x3. Okay. x1 is a cylinder given by a cylinder. Wait, S1. S1 is the side given by a cylinder and then cut by what? Cut by a disk. Okay, s squared plus y squared less than or equals to 1. S2. S2 is at the bottom here. Okay. And then S3 here is a special one. It's a plane. Z equals to 1 plus x. Okay. 1 plus x. So you use a plane. Z equals to 1 plus x. Cut the cylinder. Okay. You have a cylinder, but you cut it with a plane. So you get this shape here. Okay. So there are three integral here. Three surface here. Okay. So let's write down the three surface. X1 is given by x squared plus y squared equals to 1. Okay. How to give a parametrized surface here? Polar coordinate. Using polar coordinate. Not exactly polar. Okay. Yeah, cylindrical. Okay, but the cylindrical here only controlled by two variables, right? Okay. Yesterday we briefly go through this. Okay, so we can control by angle and the height. Okay, we just control by angle and the height. Why? Because the radius already fixed. Okay, there's only radius 1, so you need to add extra radius. Right? Cylindrical, you need what? Angle, height, and what? Angle, height, and what? Cylindrical. Radius. Okay, so radius here is just 1. Okay, so you don't need the extra radius condition. So this one is rotate around xy plane. Okay. One more thing is this vector calculus, right? Combine everything you have learned. Parameterized curve, partial derivative, multiple integral, okay, everything. So this is also the longest time I spent to do your lecture notes because it includes every technique inside there. Okay, so you need to put everything together now. Okay, so because this is a cylinder on xy plane, right? Okay, so you have cos theta and sine theta on xy plane so that they rotate around xy plane and then grow in the z direction. Okay. But what's the range you need to take? What's the theta you need to take? Okay, because you take the full cylinder. How about height? 0 to 1 plus x. So 1 plus x in this case is what? In theta form, theta z form, what is x? Okay, x is cos theta, right? So this is the change of variable you did. Correct or not? X equals to cos theta. So here I put here x equals to cos theta, y equals to sine theta. Make sense or not? Change of variable. Okay. Okay. Can see or not? Z bottom bounded by 0, above bounded by z equals to 1 plus x. Okay, so z is less than or equal to 1 plus x. But x in the theta and z form is what? Is cos theta. Okay, x equals to cos theta, y equals to sine theta, z. Okay. Where to add 2? X equals to 2 cos theta, y equals to 2 cos theta. Yeah. So in general, you add the radius at the in front of sine and cos. Okay. So this is S1. How about S2? I think S2 is easier, right? S2 is the this. Okay, S2 is a this. How to parameterize a this? I think you can use XY as well, but polar coordinate I think is easier to calculate, right? S2 is what? It's a this. Okay, it's a this. How to parameterize this? It's similar, right? So this one, okay. Let's see. You see, there's a weird thing coming out here. So you see here is similar equation. Okay. So but here we consider this thing as a cylinder. Right. So we consider all the height. Not all the height, but cylinder cut by z equal to 0 and z equals to 1 plus x. But at the bottom here, we only care about this at z equals to 0. Okay, if you want to parameterize this, right? So this is just cos theta sine theta z equals 0. But where's the range? Okay, so the range is but you need to consider. Okay, so what do I want to say here? But this one is just a circle, right? Is it just a circle? Okay. So instead of introduce z, right, we should introduce the radius. Okay, because we want the radius from 0 to 1. Because the disk contain radius 0 to 1. But z here doesn't matter. Z is always 0. Okay, we don't need to care about z. Okay, what is changing here is radius and angle. Okay, here is radius. So I put an R here. Maybe put rho. I'm confused. Okay, rho here. So rho, so the domain here is rho is in between 0 and 1, and theta is in between 0 and 2 pi. Okay. Why we don't want z here? Because the z is not changing here. Okay. What is changing is radius and also angle. Okay. Can make sense or not? Can. Okay. Next, how about x3? Okay, x3 is a plane. X3 is a plane. Okay. X3 is just a plane. So plane, maybe we just leave it as a plane. What do I mean is I can write it as x, z. Let me see how to parameterize this. XY, sorry. Okay, so my x is x, my y is y, and then my z is 1 plus x. So this is the standard function. If you see the note, right, they keep writing z equals to fxy. This is an example of z equals to fxy. Right, so you see z equals to function in xy. There's no y here, only controlled by x. So this kind of pattern, right, usually you just write it as rxy equals to x, y, and fxy. Okay, in our fxy here is just 1 plus x, so we put 1 plus x here. Yeah. Okay, and then what's the range of xy? What's the range of this? Anyone know what's the range of the xy we use? It's just the circle. Okay, so this xy need to satisfy the x squared plus y squared less than equals to 1. Okay, need to satisfy the circle. this equation. Yeah. If you want to straight away write this in polar, also can. Okay, up to you. If you want to write it as polar, also can. Okay. Okay, next. So we need to do surface integral here. So there are three part you need to do. So because this surface agree on boundary, right? We can split it into three part. Okay, we split it into three part. So meaning if I integrate the whole surface of z dx, okay, we can split it into three surface integral. Okay, we split it into x1 z dx plus x2 z dx plus x3 z dx. Okay. Okay, let's do one of them, x1 first. Okay, so x1 we parameterize it using theta and z. Okay, we're using theta and z. So we need to write d theta dz. Okay, and then what's the range here? Theta is going from 0 to 2 pi, and then z is going from 0 to 1 plus cos theta. So I need to change the orientation here. Okay. Okay, so z here is still z. Okay, we are still using z variable. Because we use parameterized curve, right? Yesterday we said that if the surface is curved, how we make it flat to compute the area? What's the thing we use to make the rectangle flat? How to make the rectangle flat? What's the factor we are using? Huh? So you are integrating over a curved rectangle, right? So how to make this rectangle flat and then compute the area? RV, the tangent vector on your surface, right? And then you take the cross product and then you compute the length. That's the Jacobian. Remember? Jacobian. Okay. So what am I saying is this factor here. Okay. Length of the cross product of two tangent vector. This is the Jacobian that counts the area of the rectangle. Okay. Okay. So remember this. This is similar to the line integral. Line integral, you only have one factor, which is the derivative of your vector function. But now here you look at the tangent vector. Okay, cross product of tangent vector. But cross product of tangent vector is a vector. You want a scalar. Okay, so you take the length. Yeah, not. Okay, you take the length. Length of a cross product. Cross product between who? Between two tangent vectors. Okay. Okay. So in this case here, our variable is theta and z. So what are the two tangent vector you want to take? We have theta and z here. What are the two tangent vector you want to take? Tangent vector with respect to theta and with respect to z. Okay, tangent vector with respect to theta and tangent vector with respect to z. Okay, so what is our R here? Okay, how about we do it here? Okay, so we compute what is R theta prime, okay, and R Z prime. So if you differentiate R theta, what do you get? With respect to theta, you get minus sine theta, cos theta, and 0. Okay. How about RZ prime theta? You get 0, 0, and 1. Okay. If you cross these two vectors together, what do you get? Most of them are just 0. Okay. Most of them are just 0. I didn't do anything wrong, right? Did I do anything wrong? Yeah, I didn't do. Okay. So when you cross them together, what do you get? Cos theta, sin theta, and 0. Okay, cos theta, sin theta, and 0. So you want to compute the length of this vector here. This is what? This is a unique. You need this. You need this, right? So what is the length of a unit this? 1. Okay, cos square plus sin square equals to 1. So this is just 1. Okay, so the factor here is just 1. Make sense or not? Okay. So the factor you need to introduce here is just 1. Okay. How you remember this factor, right? You need to remember what we did in line integral. Okay. But now we have a vector tangent vector function. Okay. So if you integrate this, what do you get? You just get z squared over 2 integrate 1 plus cos theta 0 of d theta equals to integrated this of 1 plus cos theta squared over 2 d theta. Okay, so then you need to do your double integral step, double angle step. Okay, so I just straight away replace it with double angle formula. Okay, then you can just do integration. Maybe I will go quite fast. Don't just copy. Check the step makes sense or not. Later I'll post it up. You just need to check whether the calculation okay or not. And what I say is okay or not. Don't copy because I will go quite fast. Okay, so if okay, then we proceed with the next one. So let's do, yeah, question. What you want to do? What you want? Yeah. Okay, how about x2? How about x2? How to do x2? Okay. So similarly, you also need to get the theta and phi out. Okay, you need to get the theta and phi out. What do I mean by theta and phi? You need to compute their tangent vector. Okay, let's compute the tangent vector. Let's compute a tangent vector here. So what's the tangent vector with respect to theta in this case? Minus rho sine theta and rho cos theta. Okay, 0. But how about rho r rho prime? You get cos theta and sine theta. And then 0. Okay, so what's the dot product between these two? Do you know? What's the cross product between these two vectors here? Huh? So, got one term. Let me try. So you got so this is the last term, right? 0, 0, and 0, 0, and what's this? What's this? Rho sine square theta. Minus this one minus rho cos square theta. Correct or not? Correct. 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 So here, so this one, this cross product here. Okay. For the rest, you need to multiply with these two zeros, so you always get 0. Correct. Can follow? Okay. What is this? This is just 0, 0, and minus rho. Okay, minus rho. Okay. So what's the length of this? It is just rho. Okay, it's just rho. Okay, it's just rho. Okay. So let me repeat again. Okay, repeat again. So if you want to integrate over x2 of z dx, you need to change your integral, in our case, to d what? D rho d theta. Okay, correct now. We use rho and theta here. D rho and d theta. D rho going from 0 to 1, theta going from 0 to 2 pi. Okay. Rho going from 0 to 1, theta going from 0 to 2 pi. Okay. But z in our case is what? Is 0. Okay. Multiplied by our Jacobian is rho. Okay. So 0 times rho is 0. So integrate over 0 is 0. Okay. So there's no contribution here. So it's 0. Because our plane is z equals 0, but our function is z. So z have no contribution. See, our function is z, but on the surface z is equal to 0. Again, no contribution. Make sense or not? Okay, make sense? Okay. Okay. Yeah. Which one? The what? Okay. Yeah, the length. Yeah. Yeah. How to compute the length? You take the dot product of the cross product. Then you square root it. So square root rho minus rho square. You get rho. Okay. Okay. Yeah. Okay. Last one. Okay. Last surface. S3. Okay. S3. So X3. X3. X3 is already XY, right? So we don't need to do the Jacobian. If you do the Jacobian must be 1. You believe me or not? Why you so easy believe me? Yeah, normal integral, because we are just doing on XY plane. Okay, so XY plane, the rectangle is already flat. So if you do the Rx, Ry, and then cross product, and then do the length, you should get 1. Okay, so we can straight away do the integral. X3 of z dx. Okay, so we make it into dx dy. So dx is what? Dx, wow. Now a bit dangerous, because we are integrate over a disk. Okay, but z become what? Z become 1 plus x. Okay, x. Hey, actually seems like there's a change here. There's a Jacobian involved here. Why? Why there's a Jacobian involved here? Why is there a Jacobian here? Then let's try and compute this Jacobian. Seems like there's a Jacobian here. Why is there a Jacobian here? This is a plane. This is a. Oh, I think. Okay, wait. So let's try again. Let's compute this. See Jacobian is 1 or not. Let's check what I said is correct or not just now. So let's check the Jacobian. So let's do Rx prime. I prime. Check these two. Let's check these two. 1, 0, 1. And 0, 1, 0. Okay? Correct or not? Okay. So let's check this Jacobian. Is it 1? What is Rx prime time Ry prime? Then you got 1 on the 0 position. You got the middle one is 0. You sure? Okay, so you do AD minus BC, you get this, and then AD minus BC, you get -1. Right? And then you get minus AD minus BC, correct? This is 0. Hey, actually there's a factor here, correct? 2, okay? Not 2, square root 2. So the length of this is square root 2. Okay, I think I know why. Okay, why? Because this rectangle, right? I think because this rectangle here is not the surface lying flat on the xy plane. Right. So this is a slanted z equals to 1 plus x. So your area is like this. You get what I mean or not? So it is like you imagine there's a circle here, and then it like get how do I say it? How should I say this thing? So let me see, how do I say this? Okay, let me say this. So so what is this? Okay, so what is this circle here? This circle here, okay? This circle here, you can think of it as an image of the bottom unit this. Okay, you map the bottom unit this up to this here. You can imagine what I say. So you got a this here, okay, and then you send it out like this. A little bit. So you have a bottom, have a unit this, but the plane equation send this unit this to something like this. Yeah, can you imagine or not? Okay, so every time when we say flat, right? Flat, you really have to stay on the xy plane. Okay. Otherwise, if you compare back to something on the xy plane, it will change most of the time. I mean, yeah. Okay. Yeah. I mean, to be safe, right? You just compute the tangent vector. Okay, just compute the tangent vector. Okay. No. Sometimes the transformation will just give you. Sometimes you also have transformation, but the transformation also transformed by factor of 1. Not most of the cases, some of the cases. Yeah, some of the cases. In general, should change. In general, should change. Okay. For example, if I just leave this, this out, right, it should be still the same. Right? But this is different. This it sends to some slanted this. Okay. Because if you don't increase the this, right, you won't fill out this shape here. Can you imagine or not? Do you eat Pringles or not? You eat Pringles, right? Okay. So how do you take the Pringles out? Shove your hand inside, or you take it like this, right? Take it out like this. Because why? Because if you move the units this out, you won't fill out the radius. Okay. So this means if you want to fill out the radius, you need to make the Pringles larger. Right or not? If it is slanted. Makes sense, right? Okay, that's why you take it slanted. So you take the sprinkle out. Okay, you don't take the sprinkle out like this, right? Because your hand also cannot fit. Okay, so you need to take it out first and then you take it out. Right or not? Okay, so this means what? If you want to fill out the slanted radius, you need to increase the area. Okay, so in this case here, we increase by square root 2. Okay, can you imagine or not? Can you imagine? Okay. But you what? But you're reluctant to accept. Yeah. Huh? Change. The shape change. What do you mean?
I have parallel to one plane if I calculate the surface.
No. The problem is all these points are coming from a unit circle. That's all. You can think like that. Yeah. Either you squeeze it back, either you squeeze it back, either you send it forward. Different topic. This is just a transformation.
So if I like
lifting
out, but the radius is same.
Lifting out radius is same. Then you don't change. You don't change the area. It's the same area, right? You don't change, right?
So can I simply say if my surface is parallel to my face, then I don't need to change?
Yeah. Definitely.
If it's not parallel, then I have to change.
Yeah, right. Because you are using the same this equation, right? Okay, but here we are not using the this equation. No. Here is what? Here is the plane equation. No. We are integrating the plane equation. No. But the domain is the this. No. But what you do is you integrate over the this. You integrate over the this, but your surface is also a this. Okay, but now here is a surface cut out by the plane. Okay, so yeah, okay, yeah.
So my integral is based on the surface, then my domain is something else.
Your dom, yes.
But if you cut like, but the radius did change also same one, right?
Say again.
You cut with the plane, but the radius didn't change when you did.
Why?
Because you leave out the radius quite bigger. Right? If like I still cut with the same plane, but I leave out with the same radius.
Then if the radius is the same as the this, then you don't have a Jacobian factor. Yeah. Here got because why? Because you can imagine that the this already increased in size. Sorry. Yeah, you just do the tangent. Yeah, the cross product of tangent method and then compute the length of the cross product. Okay. If you are not sure, you just do it. Okay. If you are not sure, you just do it. Okay. Not sure, just do it. Okay. Okay or not? Okay. Okay. Yeah. Okay. So okay, so we need to change variable. Okay, what do we need to change? So so we over this, and then actually there's a Jacobian factor here, so it's a square root 2. Okay, so you want to integrate over a this one. Okay, so the easiest spherical the coordinate to use is what? Polar coordinate. Okay, so we turn it into polar coordinate. So this is using chapter multiple integral. You want to integrate over this, so we use polar. Okay, so this is a this, right? Radius is just bounded below by 0, bounded above by 1, and then you take all the angle. Okay, recall what's the polar coordinate variable change? X equals to what? R cos theta, y equals to R sin theta. Okay. All right. So you go from xy plane to polar coordinate. You also need a Jacobian. Okay. So what's the Jacobian? R. Okay. So you need to introduce R. Wow. Put everything together already. R d r theta. Okay. X become R cos theta. Okay, I think this integral is quite simple, right? Yeah, this integral is quite simple. So the hard thing is to put the domain together, the Jacobian together, okay? Area of the rectangle. Usually this integral should be not too hard. So the first step we got R squared over 2 R cubed. Okay. You finish computing already. You got the final answer already. What do you get? Yeah. Okay. So let us continue first. See we got the same answer or not. Don't just keep copying. See what I wrote is correct or not. Okay, so how many number we get? So the first number we get is 3 pi over 2. Okay. The second number we get is 0 because z component is 0. Third number is the square root 2 pi. Okay, so altogether we have 3 over 2 plus square root 2 pi. Okay, any question or not? Any question? Any question? 9 o'clock, we got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. 11 page to go. Hopefully we can introduce a bit ODE before we left today. No, plus ODE. Okay, so let's take a break, short break until 9 o'clock. Yeah, 我看一下哪一个？3 yep. S3 因为我们怎样做这个东西出来，其实我们就是用这个做出来的。OK， 你是说它 D 为什么是这个地方？因为 因为如果你 project 下去的话，它就是这个 disk。
已经 expect 了要 project 来转到那个 domain 了，还是你是看着
有看到我删你给你，
对，因为我要 set 我的 domain as 那个 disk。
这个下面这个地方？
Yes。不然你怎样形容它上面的点？我问你。
是这种是吗？
对对对，所以我们讲形容上面的这个点呢，它是从下面的 unit link 上来，所以 that's why 刚才我们 skip 了这一步，就是说它是从这个原本的 disk 被拉上来的。Yeah。
你的是什么的话，这样我就不用打了，这个呗。就因为你 calculate 的 domain 是在这里，所以你要把它放上去。
不可以没？我觉得你再讲一次，你刚才讲吗？
因为我们现在是用这个 domain 嘛。
你讲假设如果我只用这个 unit disk 的话，啊，
假设的话，calculate 到
嗯哼，
这样的话不是不用解头针？
可以呀，可以没？I mean。不是你讲那句话的意思是什么？OK，假设不要看这个啦，假设就 integrate over 这个 unit disk 就好了。OK，我的 R 就是这个 unit disk，好不好？这样的话，什么叫做 calculate 那个 area？对吧？你刚才讲嘛，你讲 calculate 那个 area 就好了。Yeah。
我这个设备下去这里不用这个人 domain 哪个？
没有，我刚才的意思是，那个是洪明讲的东西，我讲的东西是我从这边 project 上来，然后我算上面的东西。所以我才讲它有了一个 area change，为什么呢？因为如果你要从这边变成这个的话，你肯定这个圈会变大的，对不对？而且这个是一个 one to one transformation，其实要用那个 one to one transformation 的，的那个来解释，那个结构边才会调出来。one 的 transformation，这是一个 one to one 的 transformation。是这个，哎，这个是 linear actually，呀，linear。呀，这个是一个 one to one 的 transformation，但是有一点奇怪啊，因为它的 transformation 是用 beer，也不会奇怪啊，其实这个就是 one to one 的 transformation。呀，就是它从这样子变到这样。嗯，听不是很，
double integral 跟这什么分别
跟这个有什么差别？一样啊，一样啊。multiple integral 就是 double integral 的话，就是在算那个 domain 上面的 volume 嘛。但是这一个是我们把那个 double integral 换成 s。换成 S 的意思是说，我不只是算 XY plane 上面的 volume 嘛，我是算每个 surface 上面的 volume，可以理解吗？OK，正常的那个 double integral 啊，那个我们每次切那个什么 cube 啊那些啊，那些是活在 XY plane 这个平的上面，XY plane 平的上面，但是这个 surface integral 呢，是活在不同的 surface 上面。一开始我们只可以站着好好的算，但后来我们可以这样斜斜的算啊，怎样斜斜的算呢？要用那个解扣边呢，把斜斜的东西移回直直的东西算，平的东西算，OK 吗？这个其实要用 change of transformation 来解释，等一下我再解释。
每个算的东西都是它的 volume。
对，没错。我不可以这样子跟你讲啊，I mean， 也不是 volume，不是什么 volume 呢？这个 volume 是有一点抽象，因为这个是一个也不抽象啊，其实。OK，你要怎样想这个东西？你要怎样想这个东西？这个东西，这东西不能想呀，我觉得能不能想啊？这样子，你这样子，你这样子，你这样子，你这样子，你这样子想，我觉得这样想啦。你看啊，它 over 一个 surface 啊，你有一个 z axis，可是这个 z axis 又不是很准确，你知道吗？所以你就可以想象这一个上面我有点，然后我有一些东西这样，然后 over 这些一圈上面我也有一些点，好像一些 buff 啊，还是 aura 这样啊。OK，如果你们玩 game 的话，可能用这些字表啊。所以你 over 这 surface，你每一个点都有 weight，OK，然后你 integrate over 这个 aura，然后这一 side 呢，这一圈呢也有 aura，下面一圈呢也有 aura，所以这整圈这样。
对，我算的是
哎呀，可以等这样，
所以算的是什么？
是你旁边的那个金光，
红八福，红八福。
就是你 over 这个 surface 上面你有一些 weight，然后你 integrate 它，
因为这个是零啊，我还是不明白啊。
哪个是零？
有一个直接零的，有一个直接等于零的，你讲它没有影响到的。
哦，因为你看，因为我的 surface 这边是零，所以我 sub 那个 z 的时候 z 要 sub 什么？
其实它的这个图像啊，它是怎样？它就是在这个 x 这边，就是在这条线，在
对
这条线，它这边还有一个弯曲。
对，
那它这个弯曲的点是在哪里？就是
什么意思叫弯曲
OK，它现在是
你
OK，
要讲它切在哪里啊？
没有啊，OK，它现在是它跟你讲这边上面是一个 C 零的嘛，
对
不对？但是它的图像你看这边还有一个弯，
这个是 ceiling，这个是 circle 啊
所以它就是 C 零的这样子接就是假设就是
，plane 切 cylinder 嘛，
就是这样子
这样
被砍到。
就是切下去，砍下去，这样砍下去
可是如果我这样看下去，为什么它这边会有一个来？
，intersection
不是三点 intersection，你看它讲它的底部是
底部是 this，
s square，这个嘛，就是有一个 square，就是说它是会慢慢收缩嘛，是吗？
没有慢慢说是全部 this 我要，全部我都要，全部小于等于1的我都要。
哦
，OK，这样。
对，
等下再问，如果有的话。Okay, so just now I talked about this radius change, right? The accurate way to think of this is the one-to-one transformation. Okay, one-to-one transformation. So where is the one-to-one transformation? The transformation is from the bottom unit disk to this cut surface here. Okay, so this is a one-to-one transformation. Z equals to 1 plus x. Okay, so this is a one-to-one transformation. So one-to-one transformation, you need to have the Jacobian. So the Jacobian here is exactly the area of the parallelogram. Okay, or the trapezoid and so on. Okay, so this is the one-to-one transformation. You change from the domain, you need this to this cut surface. Hey, where's Lin Tianyang? Huh? He never miss one. Oh, later he present. He also scared presentation, man. Scared the teacher. Why the teacher so? Okay, so let's come back to this oriented surface here. So what's the oriented surface? So to define surface integral of vector field, we need to rule out the non-orientable surface as the Mobius band. Okay, so yesterday I showed you this Mobius band, right? Okay, so if you take a strip, okay, you turn it around and then you combine it, you attach it, okay. Okay, you attach it. If you choose an orientation, okay, if you choose an orientation, and then you go around this Mobius strip, okay, and you come back to the same point, then this orientation will change. Okay, so this is not orientable. Okay, understand or not? Okay, I pass this tool to you. You can play around with this. Okay, then later pass me back. Okay, so you can start. There's a dot. Let me show you. Yeah, let me show you this. Okay, so if you start with the dot here, okay, if you start with the dot here, okay, you choose an orientation. There are two orientations you can choose, right? Across the plane, there's a normal vector. So then normal vector either go up or go down. Okay, so if you choose one of them, and then you go around the strip here. Okay, if you go around the strip, okay, so because I had no hand, so I just tell you. So, okay. So I try again. Later I will pass you this tool. You try yourself. Convince yourself there's non-orientable surface. Okay. So I start with this point. Okay. And then I choose an orientation. Choose one. Go out or go in. Okay. Go out or go in. So I choose one, and then I go around this surface here. So let's see. Then I move along the strip. I move. So I move. So I move. Okay. I move. And see a lot. I move. Go in here. Yeah, I move. Then keep moving. Okay. Keep my orientation right. And then what I do is I reach the green dot already. Okay. But I start with a red dot. I start with a red dot just now. Okay. Back dot is the green dot is at the back. Okay. Just now I start with here. Okay, I start with here. So I go to the green dot at the back. Okay. Okay. So Mobius band is the thing has only one side. Okay, be like Mobius band. Yeah, one side. Only one side. Yeah, only one side. Be a Mobius band. Okay, let me pass down. You can try and convince yourself. Okay.
So you kind of larger Mobius band, right?
What do you mean by largest Mobius band?
Larger. You kind
Pass. Huh? What do you mean? Okay. Okay. Yeah. What? Saturday. Why? Continue first. Rush first. Okay. So orientation. Yeah. So why we consider orientation? Okay. So there are two possible orientation, going out or going in. Just now I already tell you. Okay. So how to find a normal vector? We already know, right? We just dot product. But if you want a unique normal vector, you just divide by the length. Okay, divide by the length if you want a unique vector. Yesterday I told you how to differentiate going out or going in, right? Okay. Only when the surface is equal to z equals to fxy, you can determine it clearly. Okay. If your surface can return as a form z equals to something else, then if k is positive, then it is outward. Negative is inward. Okay. Because z, yeah. Okay, I don't want to say because. So continue. Okay, okay or not? Only when z equals to something, you can decide from the vector of normal vector. Okay. Because it follows the direction, either it follows the direction of the surface or it doesn't follow the direction of the surface. K, K. Okay, I mean, let's give you an example, right? So let's give you an example. Z equals to 1 plus x. Just now we see one. Okay. What's the normal vector of z equals to 1 plus x? Hey, very good. 1, 1. Wait. You sure? Okay. I can write it as wait first. I can write it as minus 1, 0, 1. Okay. Why I choose this? because just now as we see that this plane is like this. Okay, so this is, you see the Z here, 1, okay, the K here, the K part here is greater than 0. Okay, so it is outward, right? Okay, if we choose the negative one, it is inward. Okay, so let me write a label here, outward, and this one is an inward. This is the definition. Okay, definition. Okay, definition. We take this as outward, take this as inward. Okay, outward following this one, inward I put -1. Okay, 1 0 -1. So let me label this line here. This is a 1 0 -1. Okay, okay, this is definition. Definition. If I have this surface here, okay, if this is positive, okay, then this is outward. Negative, then inward. Definition. Definition. Don't ask me why is this true. Definition. This is definition. Okay, so you need to accept this. Because there's no why already. Sometimes you ask why until one step, right? You need to fix something. Yeah. Okay. Okay. So why we care about this? Okay, why do we care about this? Because we want to do integral on curved surface now. Okay, let's say we do integral on loops, right? We join the line together. Now we want to join the surface together. Okay, we call a closed surface. So now you can roughly see why we call the outward positive. So if the positive orientation is the one that the normal vector point upward from E, okay, we will call this upward from E, a positive orientation. If everything go inside, that means it is negative orientation. Okay. 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 Then now we will introduce surface integral for vector field. Okay. So vector field is a vector. Okay. Vector field is a vector. So how to integrate a vector? How to integrate a vector? Okay. So we need to integrate this vector field on a surface where we take the dot product between surface and integral. Okay. So when we take the dot product, right? In line integral, what's the things that pops up? The arc length, okay, or the unit tangent vector, okay. But how about here? Surface. What vector attached to surface? Normal vector, okay. So you dot your vector field with your normal vector, and then you do the surface integral. Okay or not? Can get it? Okay. No. Okay. Let me recall for you first. So what's the line integral? Line integral of f. Work done. Okay. Let us talk about the work done. Okay. Work done is what? We take f dot with the r prime, right? We dot with the r prime. But here we dot with the normal vector. dt. Yeah. Correct. Good. Okay. Yeah. Okay. So here, who replaced the r prime? The normal vector. Okay, the normal vector. Okay, makes sense or not? The normal vector, because the normal vector, how you get the normal vector, is also a cross product of tangent, two tangent vector. Okay, yeah. Okay. 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 Yeah. So the form here, this integral is called a flux. Okay. Line integral we call a line integral of what? Vector field we call work done, and then surface integral of a vector field we call flux. Okay, flux. Flux. Okay, we call flux. Okay. Okay. How about try one example? Okay. Not so much, also no example, right? So do example first. Okay. Evaluate this flux. Okay. Evaluate this flux. So you have a vector field on this surface here. This surface is what? Bounded by z equals to x1 minus x squared minus y squared and z equals 0. Okay. So how many surface you have? 2, x1 and x2. So we need to do parameterize surface. Okay, let's parameterize this surface here. So x1, is it easy to parameterize or not? How to parameterize this surface here? How many variable you need to parameterize this surface? 2, okay, x and y. Okay, r, x and y. So first is x, second is y, third is 1 minus x squared minus y squared. Why is it we can write it in this way? Because this is the general form of z equals to fxy. Okay, but the problem here is to determine the domain. Okay, what's the range of xy? The circle. Okay, do you see that this is a similar trick we did just now? Did you recognize this? Okay, so there's the one-to-one transformation from the unit this to this surface here. Okay, so you should imagine that I also got a unit this, and then this unit this get expand out. Get expand out. But we're not sure that whether this expand the area or not. So we need to check the what? Check the cross product of the unit, the tangent vector. Okay. Cross product of the tangent vector. Okay. Yeah. Okay. Can I? Okay. How about S2? Okay, I think S2 is relatively easier, right? This is just the unit this with z equals to 0. Okay, so this is the unit diff with z equals 0. So you could also write it out. R is equals to xy and 0. Okay, then the domain is just the unit list. Okay, it's okay. It's okay, it's okay. It's okay, huh? Huh? How is it okay? How is it okay? How is it okay? Okay. Uh, okay. Hey, so far okay or not? So far okay. Parameterized surface. Okay, parameterized surface. So next, we compute this integral here. F dx. Okay, we integrate this surface here. And how to integrate this surface? We need to dot product with the normal vector. Okay, normal vector. That normal vector have to be unique normal vector, right? Okay, have to be unique normal vector. All right, so let's write this down. So we have this surface here. Okay, so this one is also the combination of two surface intersect at the boundary. So we can split the integral into two. X1 union X2. So we split the integral into two. Okay. So how to do the flux? Okay, how to do the flux? So first we integrate over. So let's do the first one first. So let's do over x1 first. Okay, over x1. So what is over x1? Have to change. Maybe we do the let's do the later we will change it, but let's do the normal vector stuff first. Okay, let's settle the normal vector first. So we compute f dot with let me see. We compute f dot with normal vector first because we want to change. Why we dot? Why we dot here? Because you see, this surface here is a parametrized surface. Okay, so we want to make it into a normal area. So we dot it with the normal vector first. Okay, and then we change it to a normal area. Okay. Okay, so we dot with the normal vector. What's the normal vector here? Huh? Cross product. Yeah, cross product. So let's take the cross product. X prime cross ry. Okay. We have to divide by the length because we are considering the unit vector. You know why we consider the unit vector now? We don't want the length of the normal vector to influence our integral. Okay. Because you can scale the normal vector anything you like, right? But we don't want the influence of that. This is similar to the idea of directional derivative. We take the derivative at the unit direction. Okay, we don't want the influence of the extra vector. Okay, because we just care about direction. Okay, we don't want to care about magnitude. Okay, so what is Rx in this case here? 1, 0, and minus 2x. Ry 0, 1, minus 2y. Okay, so Rx cross Ry is what? So you get 1 in the z coordinate. Okay. What? So in the x coordinate, what do you get? 2x. In the y coordinate, what do you get? Negative 2y. Negative 2y or 2y? You have the cofactor expansion, right? Do you need to? Yeah. Okay. You get 2y. Yeah. So this is your what? This is your normal vector. And what's the length? Yeah, what's this length here? 4x squared plus 4y squared plus 1 over. What's this length? No value. Yeah, this one depend on xy, right? The length. This value depend on xy. Oh my God. 这样是这样是这样子。But everyone dead already. Dead already. Everyone dead already. Huh? 100? I think so. Yeah, your physics, engineering. I'm not sure. Homing said that he finished already. That he finished. Okay. Already. Okay. Okay. Oh shit. Then GG. I mean, huh? Okay. I was wondering, this length is so hard. Later need to integrate this or how? Huh? Symbol lab. What is your idea? Okay, let me settle this integral and then I show you on Thursday. Okay. Okay, continue first. I settle this integral, then I continue on the Thursday. Okay, continue first. Okay, I will continue this example calculation on Thursday. Okay. Huh? Okay. I'll take note. But okay, I will settle myself. Okay, next. Okay, next is the generalization of generalization of Green's theorem. Okay, Green's theorem. Yeah. So generalization of Green's theorem is a Stokes theorem. Okay. So Green's theorems only apply on XY plane. But let's say the curl live on the surface. How? Okay. We just use the Stokes theorem here. Okay. So last time I already told you that the loop integral is equal to the surface integral of the curl. Okay. But curl is a vector. So really you need to use surface integral definition here so that you can get rid of the vector. So there should be a n here. So this not a problem. So there should be an n here. Dot n. Okay, dot n. Okay. So your surface integral no longer live on xy plane only. It can live on any surfaces. Okay, live on any surfaces, curved surfaces. As long as you can find the normal vector line up with the positive orientation of the sphere. So not sphere, the closed loop. Okay, so what I mean here is, hello, wait. Hey. Okay, so in this case here, right, so we have last time we don't care about orientation of D, okay, but now we care because it is a surface integral. So when you go around the circle, you need to introduce a positive orientation. Okay, positive orientation. Okay, so this is a what do you mean? This is a generalization of Green's theorem. Okay, this surface here is any surface. So if you do surface integral here, you need to involve normal vector. So this normal vector have to be positive. Okay. So the line integral is positive, normal vector also positive. Both negative, huh? I think can. Yeah, can. Because if you have negative orientation, you will have negative sign here. But if you want to bring the negative, yeah, so to match out the two negative, you also need to have another negative. So that's me negative oriented. Okay, let's do example here. What time? 9:34. Okay, good. So let's verify this stock theorems here. So we have this vector field, and then x is this paraboloid, and then with the circle x squared plus y squared equals to 1. What is this shape, man? What's this shape? So this shape here is like this. I go back check and then I tell you. Even if ask you draw, right, it won't be hard one. Go back and check. Tomorrow, right? Tomorrow I will give you a summary and then tips. Not Thursday.
And tomorrow
Thursday.
tomorrow
Thursday. Thursday. I haven't prepared yet. Thursday. Okay. I haven't prepared yet. 是。Thursday 我会跟你说，肯定跟你讲很多，可以啊。
哇，所以都讲到这么多了，他现在每天不得给很多啊。
OK。
上飞机之前我们在聊。
OK。OK, good. Okay, so we verify the Stokes theorem. So there are two ways to compute. One is the line integral, the other is the surface integral. Okay, so we want to compute flux on the surface. It's equivalent to compute what's the attribute on the boundary. Okay, this is the fun thing of this Stokes theorem. If you want to compute something on the surface, you just need to compute something around the boundary. Why? Because flux is what? Flux is rotation. Flux is rotation, right? So remember last time I told you an idea, okay? Flux is a rotation, okay? Rotation would done in the loop direction, rotational direction, okay? So how you think of this? So you can think of this as infinitely many loops, okay? Like last time I say, you can think of this as black hole, okay? If you have two black holes comes together, what happens? They combine, okay? They will combine, okay? They will combine somehow, okay? They will combine, okay? So if you compute every loops, right? Every loops add up to the large loops, but these loops, right, live on some area. Okay, so that's why we turn this into an area integral. Okay, this loop lives on some area. Okay or not? So on one side, you compute this very small loop. On the other side, you compute the large loop. Okay, my tongue already knotted. Yeah, large loop. Okay, one of them you compute the loop, large loop, and then the other one you compute a small loop in an area. Okay, in an area. Make sense or not? Okay, curve in the area. Okay. Okay, so you keep this picture in your mind. If you forgot everything about Green's theorem, right? Remember this picture. Okay, remember this picture. That one you need to learn more. Okay. Okay, so Stokes theorem. Okay, so we want to compute two things. One is the vector field along this loop. Second is the curl of the vector field along the surface. Okay, these two things represent the same thing. Okay, as I explained just now. It's just a concept. I haven't write something precise. Okay, so line integral. Okay, line integral. What you need to do? Line integral. You need to parameterize your curve. Okay, parameterize your curve. What is this curve here? No. What's the curve of C? C is a circle, but what's the height? 1. Okay, sine is 1. Z equals to 1. And then it's from 0 to 2 pi. Okay. So you want to compute line integral, right? Line integral needs what? You need, okay, higher dimensional, we call it Jacobian, right? So lower dimensional is just R prime, the tangent vector. Okay, the tangent vector. So F applied to RT and then R prime T ET. Okay. Yeah. So you can, okay, you can also imagine as a Jacobian, right? So lower dimensional Jacobian. So R prime T is what? Minus sine T, or this one do a lot of time already. Huh? 0 to 2 pi. Okay. So F applied to RT is what? What is our F? F is Y minus X, Y times Z. Okay, so in our case here, Y is sine T, X is cos T, so minus cos T. Where? Yeah, where's the height of my circle here? This circle is at Z equals to 1. Okay, yeah. Sorry, this equals 0. Yeah. Okay, good. Okay, continue. YZ is what? Cos T sine T. Okay. Correct, right? Oh, sorry, Z is 1. So cos Y is sine T. So sine T times 1 is sine T. And then dot product with R prime T equals ET. Okay. So you just expand this. So if you expand this, you should get sine minus sine square T minus cos square T ET, which is equal to minus 1 times 2, which is minus 2. Okay. So next we will do this curve here. Okay, we will do this curve here. Okay, how to do the curve? First, you need to compute the curve of F first. What is curve of F? Okay, so you do this cross product. Fraction. Okay, all the n you get Z 0 and minus 2. So this is the curve. Okay, so this is the curve. And have we parameterized this surface yet? No, right? We haven't parameterized this surface. So what's this surface? How to parameterize this surface? This surface is Z equals to x squared plus y squared. Also, the form of Z equals to fxy. Okay. But our domain is what? Our domain is this. Okay, is this. Cut out by this. Okay. So our parameterized surface is just xy and x squared plus y squared. Okay. Yeah, so we go back to the same business, right? Same business. We want to find the normal vector to this. Hey, I really need to check whether we want to use the unique normal vector or not, because they just use the normal vector, don't use the unique normal vector. Then just follow. Just follow them. But the theorem says me to use unique normal vector. Not yet unique, right? Just now we computed. What's so bad one, this? To check. Okay, so what's the normal vector here? So we need to compute the two tangent direction. Okay, two tangent direction. So in direction of x, you get 1, 0, and 2x. In the y direction, you get 0, 1, and 2y. Okay, so the normal vector is the cross product of these two. So what do you get if you cross these two together? 1, and then minus 2x, and then minus 2, minus 2y. Okay, that's the extra minus from the core factor expansion. Plus, minus, plus. Plus, minus, plus. Okay, so yeah, so let me go back and check this unique tangent thing. Otherwise, too hard to integrate the square root thing. Okay, so I will settle the integral myself and then I show you. Yeah. Okay. So there are some more exercise. I will show you. The line integral, how do I know it's the circle? Okay, so before so we skip the integration part, I go back and check the unit normal vector part. But what you want to know now is how you decide which line to integrate, which surface to integrate. Okay, so now if you want to compute the flux over a surface, okay, how you decide the loop, how you decide the curve, which curve you take. The curve must be the boundary of your surface. Okay, so which one is your surface? The surface is the paraboloid. Okay, it is cut out by the circle. Okay, cut out by the circle or a plane z equals to 1. Okay, so the boundary here is the circle. Can you imagine or not? So how you imagine this surface here? This surface is like this. You have a disc. Okay, you have a disc. And then you lift the disc up. So where's the boundary? So the boundary is the outer circle. Yeah. Okay. So how you imagine the flux here? How do you imagine the flux? How do you imagine the flux? So over a surface, you have vector. Okay. Over the surface, you got vector. And then you integrating this contribution from x, y, and z. Okay. Yeah, right. But you are integrating everything inside one, not just one. Right? The xy doesn't just satisfy one. It satisfies everything. Okay. Yeah. Everything. Yes. Okay. So you integrate over the boundary is the same as you integrate the surface. Okay. Boundary and surface. Can follow now? Boundary of the surface. Yeah, if you go to higher dimension, but yeah, I mean, here we only deal with 2D. So you don't need to go every dimension. So we only have a surface. So a surface is like 2D. So the boundary must be 1D. Okay, because here only double integral. Okay, double integral only. No matter which Rn it is, just 2D, this thing. So the boundary must be 1D. So must be a line. Okay? Yeah. Okay, one last hardest thing from this chapter is the divergence. If I'm not wrong, this one is in the exam, but it's a very easy question. So you need to learn the basic. Huh? In the exam, but very easy question, I think, but you need to know how to calculate. Okay, so what's the divergence theorem? So this theorem contains divergence, right? So that means there's something involving the divergence, okay, or we call the Gauss theorem. So we start with a solid, okay, we start with solid, and then this one have boundary surface, like what you say, every direction. Now you got solid already, so you have a boundary surface, okay, for X. Then we also have a vector field also, okay, we also have a vector field. Let's say F1, F2, F3 have continuous partial derivative, then we have this equality here. Now, just now we relate line integral to surface integral. Now we relate surface integral to volume integral. Okay, surface integral to volume integral. But now it's the vector field on the boundary of my solid. Okay, so let you imagine like this. Okay, I want you to imagine some picture here. So you imagine a sphere. Okay, you imagine a sphere. And then above the sphere, I have vector field. Okay. And then I compute the surface integral of this vector field. How do I compute this? Okay. How do I compute this? Okay. It turns out that it is a triple integral on the divergence of f. Okay. Divergence of f. What is the divergence of f? Do you still remember the definition? Okay, then what is the property? What's the definition of a divergence of f? The gradient operator dot with the vector field. Okay, so you need to remember this. Very important. Only two ingredients in this vector calculus chapter: gradient operator and the vector field. Okay, two things you can do with two vectors. What are the two things you can do with two vectors? If you want to multiply them, you can do dot product or cross product. Okay, cross product give you the curve. Dot product give you the divergence. Okay, so now let's see why this is called a divergence. Okay, this is exactly because of this theorem here. So how do you compute the surface integral on this surface? Similarly, we can break this into smaller sphere. Okay, we can break this into smaller sphere. Okay, and then we see over this smaller sphere, okay, what's the contribution of diff f? Can or not? Okay, so if you have to imagine using sphere, you can imagine using box. Okay, so if I want to consider the surface integral of this box, okay, only on surface only. But how do I compute it? I can make smaller and smaller box, okay, with orientation, like how we make for the line integral, so they cancel out when they join, okay? And then I see how the flux, the divergence happening at each box, okay? So we turn a surface problem to a box solid problem. That's why there's an equality here. Can get it or not? This is just an idea, okay? Try and get this idea, okay? So we got this surface, and then we try to consider the smaller object, okay? Okay, so that's why they call this a diff, okay? They call this a diff, okay? That's why they define this as a diff. Okay or not? No, I mean how we relate a surface integral to triple integral. Yeah. Okay. Yeah. What's going on? What's going on? Okay. Okay. What I want to say. Okay, since we cannot do surface integral today, right? So maybe we skip the example for this one to tomorrow. So we start with body tomorrow. Thursday. Okay. Let me settle the surface integral. Surface integral, and then I will show you. I'll show you on Thursday. Okay. Yeah. Okay. And I will tell you what kind of a question from vector calculus for the final. Okay. So you just do those questions is enough, I think. Okay. I think no point going through the summary now because we haven't tried example yet. Okay. Is it okay? So I will show you example on Thursday. Okay. And then do summary on Thursday, and then give you tips on Thursday. So you need to focus what kind on the question type. Sample paper. I picked very similar one, or you guys just do it, and then that's all. Okay, so let's break until 10, then we start with all the 没有，刚才讲吧，还是 break 到8分钟。
因为我们也讲了，应该16分钟了。有不得。
Hello. Wang Zhenyong, I think I see Wang Zhenyong. 梁家瑜 not here. 李希成 okay. 刘少飞 not here. 方舟 not here. 子豪 not here. 齐哥 not here. 江宇 not here. 李杰 okay. 李培 okay. 李玉章连叶林天阳刘佳琪 I think I saw you right. 佳琪品义 told me already. 夏红 okay. 凌波香鱼彭玉玲施杰生金华子飞裴武基隆黄宇轩俊宇谢怡轩 OK told me already. 许志凯未来杨景荣 I think told me already. 张云赵静涵赵以轩周子康洪家轩 Daniel Bovin 定义 Chia Ming 恰明 not here 咩 OK 恰明 here 吕龙佩瑜 not here 宋豪以迅杰森管天明开文豪文姚琛温达一辉一顺洪明嘉盛 Rainis 永慶魏涛青柔一招何毅热人钟凯杰 OK 王雅美 I think I saw you. 郑浩伟 not here. Okay. 苏泽辉 not here. 柯志坚 not here. 哎，柯志坚 here.
你是
会修呼吁。No no. Yeah. 吴承泽。OK.
会磨到很快吗？
我也是怕
会有
买来一粒头，我不知道还好手。
多少钱你买一粒？
这个头也4年了
多少钱你买一粒头？
，10多块吧。
那你买哦
不。要买 original 的
哦哦哦哦，
我买那种特别的。
特别的，
呀，
讲讲特别，周子看。
哇，没起来。
什么？
可以中到这里中6个，都中完的。
可以中了。还有另外一张呢，有没有中吗？
袋鼠，老师就跟看路打过架。拿孩子，那孩子在我手上。
哪那孩子？
啊，袋鼠不是孩子在袋子里面。
嗯。
你打我。
啊？跳进幼儿那会怎样？
扣那边是怎样？
是啊。
然后扣那边是
不会。
打不到啊。啊，他会下来的吗？假如会下来的吗？
我没有，他就在上面躲住，然后那边没有特别细。
贴纸呢？他需要很多然后什么情况不会下来？我们贴纸嘛，我们贴纸，
他吃的那个叶子有毒啊，你知道吗 ？Eucalyptus 啊，你知道 Eucalyptus oil 吗？就是那个他们给 baby 涂那个肚子的那个油啊，白树油啊。帕拉贝什么时候会下来？火灾的时候。
我现在做什么？
逃啊！现在烧死呢。啊？不懂哎，没有人吃卡拉贝好像。
哎，为什么是 kangaroo 不要把卡拉贝塞进孩子的带他跑？拿一条蛇放进去，然后孩子就死掉。那我直接碰到最奇怪的动物，
很少看到动物的，没有动物的那边。它的山是光秃秃的，它的山是光光的。有啊，真的有啦，真的啦，它跳进来大学里面。
挑起大学呗，
他们有一股也不一样，每个大学都有，就是专门给那 category 上课。他说进去，
所以你们赶快那个波球都打
听他吹，听他吹。
一人坐这台椅子这样。
跳进来，你没有给他戴那个防水手套？有啊有啊，啊就进入的时候打成那个。
哎，天阳 ，Where are you？ 啊？你什么 ？Steve Neck。OK。OK。顶很硬 ，Steve Neck。
好像叫不到 Steve。
可以。OK。Hello. Okay, we continue with ODE. Then I resume doing the integral for you on Thursday. Okay, I resume the integral on Thursday. Okay, I resume integral on Thursday. I do ODE first, and then we resume the example on Thursday. Okay, Thursday. I will settle the dot product with a normal vector, and then I'll show you how to calculate. Okay. So let's do a second order ODE. So there's only 3 solutions you need to remember and then calculate. Okay. So what's the second order differential equation? Okay. So you have differential equation, right? So that means there is some dy dx involved. Okay. So how many order? Second order. So you only consider up to d square y dx squared. Okay. And then what kind of coefficient you have? Okay. You have all the coefficient with function in x. Okay. So all the coefficient in front d2y, dx squared, dy, dx, and y is function in x. Okay, so this is the general form. So for example, what? For example, x squared times d2y dx squared plus x dy dx plus x cubed y equals to x to the power 4, something like this. Okay. Okay, so this is the example. So there are two types. Two types. One is homogeneous, one is not homogeneous. So in linear algebra, what is homogeneous? System of linear equation. The linear equation equals to 0. Non-homogeneous equal to something non-zero. So similar here. If the right-hand side equals to gx equals 0, then we call it homogeneous. Non-homogeneous is 2x. So in linear algebra, right? So how you relate homogeneous to non-homogeneous? Solution to the homogeneous equation is also a solution to it's part of the solution of the non-homogeneous equation. So similar case happen here later. Okay. So that's mean we need to learn how to solve homogeneous equation first. There's a deep relationship, but won't tell you first. Deep. There's a deep. Okay. Yeah, not for now. Yeah, not important. So you just need to learn how to solve this one. Concept you throw away also can. Okay, so this one you need to learn how to compute. Okay, so some terminology, linear combination of function. Okay, similar to vector. In linear algebra, you take linear combination of vector. Now you take linear combination of function. Okay, what is linear combination of function? Scalar multiple of your function, and then you take the sum. Okay, linear combination. Linear is what? Linear is summation and scalar multiplication. So two operations you can take. And then two solution is linearly independent. If and only if the linear combination is 0, then all the coefficient must be 0. This is the same as the vector one. Okay. So function is also a vector. Okay, vector in the function space. Okay, so function is also a vector. That's why we use similar term from linear algebra. Okay. So for example, what are linearly independent? So for example, e to the power x and e to the minus ex are linearly independent. Okay, they are linearly independent because they cannot write as a scalar multiple of each other. Okay, these are linear. Okay, so these are linearly independent because if you solve c1 e to the x plus c2 e to the minus x equals 0, c1 and c2 must be 0. Can see this or not? Okay. If not, you can multiply across, and then you'll get something like this. Okay. So when are they equal? Only when c1, c2 is 0. Is it? Yeah. Okay. Next. What are linearly dependent? So ex and the power 2 times e to the power x are linearly dependent. Okay. Because they are scalar multiple of each other. Okay, this one just revision from linear algebra. Got question? Okay. Okay. Last semester I got. Yeah. Now we compare different two things. Two different things here. Okay 啊 ？Okay or not? Okay 啊 ？Which one? This one 啊 ？Second one 啊 ？Okay. So two things is linearly independent. We can think of it as a scalar multiple each other. But if you want to think of it this way, how do you think of it in this way? You multiply minus 2 to e to the x and then plus 1 time 2 times e to the power x equal to 0. So the coefficient is non-zero. Okay. Yeah, but it doesn't work here. Okay, it doesn't work here. It doesn't work here. You cannot find C1, C2 such that this is true. Okay, because this one implies that you get C1 e to the 2x times C2 is 0, which means what? Which means e to the 2x is equal to some ratio. It's impossible, right? How exponential increase? Increase exponentially. It's not linearly. So it is not a linear function. Okay, so this is impossible. Yeah, it's not impossible because exponential function is not linear. Okay. Okay. Yeah, this one. Yeah. Okay. Okay. So first theorem is if you already found two solutions to your second order linear differential equation, then any linear combination is also a solution. Okay, you believe or not? Believe, huh? Okay, I don't show it to you. You believe already. 当时 believe or not believe? Okay, you believe first, huh? Do I need to show you why is it true? Of course, huh? Okay, I show you why is it true. I not got, yeah, my not got. Oh, I give you the answer one. Maybe I put the wrong one. Okay, never mind. Okay, yeah. Yeah, okay, sure. Okay. Okay, huh? If can understand, we continue. What do you mean by explain? Oh, explain what I written on the my note. Huh? How about I also use that note to explain now? Yeah, let me use open out the note. Yeah, this note very blank. Yeah. Okay. Let's use this note here. Okay. So I mean, if you want to test whether something is a solution, right? You just plug that number in. See, you get a solution or not. See, does it solve it? Right. So take this. Okay. Put into your equation. Okay. How to put into your equation here? So what is depending on y here? The derivative. Okay. So you need to compute the second derivative of y, first derivative of y, and then substitute your y. Okay. But the question here is the key question here is we don't know what is PS, QX, and RX, but doesn't matter. Don't care. I don't care. Okay, I don't care. Okay. So first we differentiate twice, and first take the first derivative. What do we get? Okay, we get this 1, 2, 3 third line here. Okay, we get the third line here. Why can we do this? Because differential operator is linear. Okay, you can straight away take the scalar out and then spread into sum and then take derivative. Correct or not? If you want to differentiate the summation, the linear combination, right? You break into sum, okay, and then you. Let me write down what I was trying to say. So you break into sum first, okay, and then you take out the scalar. Because differentiation is a linear operator. Okay. Okay. Scalar is the dy dx. What do you mean? Oh, this is the linear combination. I say linear combination, meaning this is a C1, C2 are scalar. C1, C2 are scalar. y1, y2 are the solution to the original equation. Okay or not? What do you mean example? Later we'll see example. Okay, just see this theorem first. Okay, so we can further rearrange this equation here, right? Okay, so we can rearrange into two differential equations. Okay, two differential equations. But what you can see here is y1 satisfy the ODE. y2 also satisfy the ODE. Okay, so these two parts should be just 0. Okay, if you are solution to the ODE, you solve to 0. Okay, 0 times scalar plus 0 times scalar, you get 0. So that means if you apply the ODE to the solution, this y, you also get 0. So that means the y is also a solution. Okay, so you can see that the scalar, right, drop out, can be removed from the differential, can be removed from the multiplication. Okay, so it doesn't do much difference to solve the ODE. Okay, so that's why any linear combination to solution is still a solution. Okay. Okay, it's still a solution. But this theorem is more stronger. This theorem says that as long as you have two linearly independent solutions and Px is never 0 on the interval, then the general solution is this. Okay, these are all the solutions. Okay, these are all the solutions. Okay, these are all the solutions. Okay, as long as if you know two linearly independent solutions, these are all the solutions. Okay, you take the linear combination, these are all the solutions. No more already. No more already. These are all of them. Okay, this is stronger. Just now we just say if got two, I can build one solution for you. But this theorem says that these are all. No more already. You cannot find more than this. Okay, you cannot find more than this. So the key things here is you want to find two linearly independent solutions first. Then all the linear combination is the solution to it. So why two can you relate or not? Why there are two? Why would there be a two linearly independent solution? This is the second order. Okay, second order. So it's suggesting that the two has something to do with the order of this differential equation. Okay. Yeah. Okay. So next. Okay. So let's say we do an easier one. Okay, easier one. We don't want to do until px, qx, gx. Okay. Let's do just constant. Okay. Let's do constant one. A, B, C. Just do constant. So what's the solution to this second order linear homogeneous equation? Okay. So the solution only three types. Okay. Only three types of them. Okay. How to find this three type solution? Actually, we relate this to a what? To a quadratic equation. Okay, like we replace the differential with a root. Okay, we replace the differential with a root, and then we try to solve this equation here. Okay, we try to solve this equation. You know how to find the root of a quadratic equation, right? Yeah. So r is equal to minus b plus minus square root b squared 减 4ac, b squared minus 4ac over 2a. Okay. Yeah. Okay. So you will get two real root, okay, or same root, okay, or complex root. Okay. So for these three cases, you have different solution. Okay. So for the first one, okay, if it is real, they are linearly independent to each other, then you just take the linear combination. But if it is one, okay, so we attach the r to the exponent of x. Okay, we attach the r to the exponent of x. So if you only have one root, okay? If you only have one root, you only have one y, right? How to make out another linearly independent one? Okay, how do you make out another one? Not just get scalar, not enough. Scalar is linearly dependent, right? Okay, so we multiply by x. Okay, x e r x. Okay, so we have, so here we have e r1x, e r2x. These are two natural choice. Bottom one we have e rx and x times e rx. Okay, and then take the linearly independent, linear combination. Okay. Yeah. Okay. How about next one? Okay. The complex root. So the complex root you need to write in the complex form. Okay, you just write in the complex form. Okay, use it write in the complex form. Okay. So you write in the complex form. So you have this form here. Okay. You take e to the alpha plus minus I beta. Okay, times x. You know how to get this form or not? This is the Euler formula. Forgot already. Let me recall for you. E to the I theta equals to what? Cos theta plus I sine theta. Yeah. Okay. Okay. Euler formula. No, Euler formula I think is I pi minus 1. E to I pi minus 1. And then this one is the general one. I think I'm correct, right? Yeah. How do I get? How do I get? How do I get? How do I get? So you substitute your Ri into this theta here. And then you try and expand, you should get this. When you expand it out. What do you mean assiduous? Seems like there's a question here. What you do is you just follow this form here. Okay. When you do question, right? If you found complex number, you just write out this form here. And this is the form you need to write down. There are example of root that you get complex. Okay. Because you can just solve this and then you will get some complex number sometimes when you solve the root for the quadratic equation. Okay. Do you want to see why this differential equation is related to this quadratic equation? Trying to see why? See, yeah. Okay, I think this one quite important. So let's do it. But I won't show you the root one. The root one you just follow the note. But this one is quite important. This one. You can. Also can. Also can. Both can. You want to derive yourself also can. You want to memorize also can. Yeah, how to get a solution. Later I show you the example. Later I show you the example how to do it. But let me show you why this differential equation is related to quadratic equation, which we call the characteristic equation. So why is it related? So let's start with the ODE with constant scalar first. Okay. So what's the most natural function you want to think about? You want to think about e to the power x, because e to the power x, you keep differentiating, right? You get back yourself. Okay. So we try to use y equals to e to the rx to solve it. Okay, we try this. We try this solution. See if we can solve it or not. Okay, we try this. So we need y prime and y prime prime. Okay, let's see if this function here can solve or not. Okay, let's see can solve or not. So we need to sub all of them into my original equation here. Okay. Okay. So from here, right, can you see something? Yeah, can you factorize this? I take ERX out and then AR squared plus BR plus C equals to 0. But ERX can be 0 or not? There's no point for ERX to be 0, right? Okay, that means the other root must be 0, which is the characteristic equation for my second order linear equation. Okay, so for this to be 0, that means AR squared plus BR plus C equals to 0. Okay, since e to the Rx is always greater than 0. Okay. So this says what? This says that y equals to ERX is a solution. Okay, is a solution. I didn't say these are all the solutions. This is one of the solutions with R satisfying the quadratic equation. Something else, as long as you can solve it. But it turns out that the theorem says these are all of them. So the theorem just now says that these are all of them. Okay, these are all of them. This pair with another linearly independent one, then they are the solution. This is the theorem. So first I try. And then I think, so natural question is like Jason said, Jason said, is there any other solution or not? Okay. Then they found out that, oh, theorem says no more. These are all of them. Okay. ERS pair with another linearly independent one also look like ERS. So you see, all of them look like this. One of them is ERX, 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 X times ERX. Okay, and then here is a ERX. Yeah, ERX or X times ERX. Okay, if it is same root, you need to take ERX and X times ERX. If there are different roots, you just use the different two root to build your linearly independent solution. Okay. Different one? No. We haven't gone into that one yet. We just try to see why is it related to the characteristic equation. This is not example yet. Okay, let's try example. Okay, let's try example. So let's try and solve this example. So these cases, I leave it. Okay, you can read the note. How we come up with the linearly independent. So let's try and solve this. I think the final exam, the question exactly look like something like this. Exactly look something like this. Okay. Yeah. So the technique you need to know is how to turn this into a characteristic equation. How to turn this into a characteristic equation. You just replace your dy dx using r. Okay, replace your dy dx using r. So I have r. So this is equivalent to what? R squared plus r minus 6. Okay, y becomes 1. Okay, let me. So this one you don't do in the exam. I just show you. Y is 1, y prime is r, y prime is r squared. Okay, this is in your mind. Okay, this one in your mind. Okay, so why is it true? I show you already just now, right? I show you the derivation. Use ERX and then see that you need to let this equation equal to 0. Okay, so how this r drop out? Remember the process we do just now? You are differentiating e to the rx. Correct? So why is it 1 here? Because there's only coefficient 1 in front of ERX. Why y prime has r? Because you differentiate ERX once. So the r drop out. Right? So y prime, you differentiate e to the rx twice. So how many times r drop out? 2. R squared? 2. Okay, so you need to make this characteristic equation equal to 0. So what is the root of this characteristic equation? R plus 3 and R plus I minus 2. Okay, so meaning R equals to minus 2, minus 3 and 2. So this is a real distinct two roots. Okay, two distinct real roots. So this is the first case. So first case is what? It is a linear combination of e to the first root times x plus e to the second root times x. Okay, so keep this table in your mind. So meaning the general solution is, the linear combination of e to the first root times x plus e to the second root times x. Okay, so this is a distinct two root. Let's try something else. Okay, I can follow or not? Yeah. These are coefficient. You can put any C1, C2. You mean remain fully? No. All the C1, C2 you need to consider. So you cannot fix one. Yeah. Any. Where's AB? Can. Yeah. AB just represents some scalar. Yeah. Scalar. What is Isun asking? Oh, 这个? Yeah, what are you trying to say? This is not equal. I mean, I want to replace. I mean, how to get the characteristic equation from differential equation with constant what? Coefficient. Okay. So remember this one work for constant coefficient. So these coefficients are constant, right? 1, and minus 6 constant. Okay. Okay, let me show you some other things. So let me show you with same root one. Yeah, let's do this. So let me ask you, how you replace this differential equation with a characteristic equation? What's the characteristic equation? 4 y squared r squared plus 12r plus 9 equals 0. Okay, so how to solve this? So this is 2r plus 3 squared. Okay, so r equals to minus 3 over 2. So r equals to minus 3 over 2, right? So there's only one root. So how do you find two linearly independent solutions? C1 e to the minus 3 over 2x. How about the second one? C2 of what? X times e to the minus 3 over 2x. Okay, so this is the general solution you have. Okay. Okay. Okay, the logic is very simple one. So how to solve this one? So what's the characteristic equation for this? R squared minus 6r plus 13 equals 0. Okay, so this is a complex root actually. So you compute the formula minus b plus minus square root b squared minus 4ac, okay, over 2. So what you get is 6 plus minus 36 minus 52 is what? 16. Minus 16. Okay, minus 16 over 2. And altogether you get 3 plus minus 2i. Okay, so what's the general solution here? Okay, if you can go back and look at the table, you have what? E to the power ax, okay, is 3x times c1 of cos 2x plus c2 of sine 2x. Yeah. Okay, so you solve this. So 6 plus minus 4 times square root minus 1 over 2. Calculator can put I now. I thought last time square root might negative or error. Calculator can. Only one can. Okay. Okay. So just now you ask C1, C2 can fix or not? Okay. C1, C2 can fix if you have an initial condition. Okay. If you have an initial condition, then C1, C2 can be fixed. Hello. So C1, C2 can be fixed when the initial condition is given. Okay. Initial condition is given. Okay. So if you have initial condition, then C1, C2 can be fixed. Okay. Can you imagine what I say or not? Okay, if not, let us do this. So the characteristic equation for this differential is what? A plus R minus 6. Okay, so what are the roots? Okay, I think we saw this before, right? Yeah, we saw this before. So the general solution is y equals to C1 e to the minus x 3x plus C2 e to the minus 2x. Okay, but we want to satisfy this initial condition here. So y at 0 must be 1. So it implies what? 1 is equals to C1 plus C2. Okay. Second condition is y prime 0 has to be 0. So let's look at what is y prime first. Y prime is what? Minus 3C1 e to the minus 3x plus 2 times C2 e to the power 2x. Okay. Y prime 0 is what? Is 0. So on the other hand, we got negative 3C1 plus 2C2. Okay, so we got two equation, system of linear equation here. Okay, we got a system of linear equation. So we got the second one, we got the first one. So put the second to the first one, we get 1 equals to 2 over 3 C2 plus C2, which is C2 equals to 3 over 5. Okay. And then we sub it back to 2. Okay, sub this one back to 2. So in the end, we get C1 equals to C1 equals to what? 2 over 5. Good. Okay, so the solution, the specific solution is y equals to 2 over 5 e to the minus 3x plus 3 over 5 e to the power 2x. Okay. So if you have initial condition, then you can find your C1, C2. Yeah. 10:37. Okay, keep going. Okay, continue. Okay. Non-homogeneous linear equation. So we already solved the yeah. Yes. General, yes. So yeah. So meaning if you change the initial condition, right, you might change your solution already. Okay. So you should think of this, right? So how to relate to calculus? Typically, when they solve this differential equation, right, they want to see the rate of change of something else. Okay. And then they want to find the solution, meaning what curve satisfies this change. Okay. What curve satisfies this change? But general solution says that there's a lot of curves that satisfy these changes. Okay? There are a lot of curves that satisfy the changes. But if you start at some point, then you need to follow this curve. If you start at different point, you need to follow different curve, different CY and C2. Okay? So changing the initial condition, meaning you start with which point? Okay? Start with this point, there's a solution to it. Start with the other point, there's a solution to it. The two lines are different C1 and C2. Can you imagine or not? Okay.
Typically, this one classical example for differential equation is wave. Wave, okay, wave equation. Okay, one typical example. Okay, can come back. So just now we saw homogeneous linear equation for with constant coefficient, right? Now let's solve non-homogeneous one. Okay, so like what I said just now, this is really similar to linear algebra. So if you can solve the homogeneous linear system equation, the non-homogeneous one will include the solution for homogeneous. Make sense or not? Okay. So similar to linear algebra, you have this formula here. So how to find the solution to non-homogeneous linear equation? You add two solutions together. Okay. One is a particular solution to this equation. The other one is the general solution for the homogeneous equation. Okay. Okay. You know why? Do you know why or not? You know why is it true? Even from linear algebra? Don't know what? Okay. So let's say, you see, so if I apply this function, so if I sub this answer into my differential equation, what do I have? I split into two parts, right? I split into d of yp of dx squared plus b of dyp of dx plus yp equal to g, sorry, not equal, and then plus a times dy d2yc dx squared plus b times dyc over dx plus yc. Correct or not? Can I split like this? Can I split like this? Because differential operator is linear, right? So I can split like this. But you see, the first part is the solution to this particular solution to this equation. So what do you get? So the first part here, you get what? What do you obtain for this equation here? This expression here? Not zero. This is a particular solution to this non-homogeneous equation. So if you compute the left-hand side already, you get gx, okay? Gx. But how about this one? This is a solution to homogeneous equation. So what is this? What does this equal to? Zero, okay? But gx plus zero is what? So we can add the homogeneous equation solution in, because it doesn't change my solution. Yes. This person, so we want to try and find everything. Okay. We not just want to find one solution, not enough. Okay. I want to find all.
Another homogeneous.
Still zero,
But still solution.
yeah. Not enough. We want to find all. You know already. Huh? You get it, Okay. So we only learn one method. The note you see got two methods, is it? One is the undetermined coefficient. The other is variation of parameter. We only learn one. Okay. Undetermined coefficient. We only learn one type. Okay. So how? So what's this question? So how to do this? So okay. So this method here, right, depend on what GS you have. Okay, what GX you have. So you see, you want to solve this linear equation, right? Okay. What's the first thing you will put on Y? Okay. What's the thing what's the Y in terms of X function you want to put? Okay.
You want to be able to compare the left and right. Okay, the right is x squared. Is it possible you put x cubed or not? Because if you put x cubed, no one compare with x cubed later, right? Okay, so the highest thing you can put is x squared. Make sense or not? Even if you put x cubed in, who gonna compare with x cubed? X cubed must go to 0 in the end. Correct or not? Okay, so you put the highest degree, the gx that appear on the right hand side. Okay, right hand side. Okay, so let's solve particular solution first. So maybe our yx will be something ax squared plus bx plus c. Okay, we don't know whether we want to make the lower degree to be 0 or not. Okay, but at least we need to compare x squared first. Make sense or not? Make sense? Huh? Does it make sense? Does it make sense? Okay. Okay, I repeat again. So if we have this system of linear equation, right? Can you guess what kind of y we want to put in? Guess. You must guess one. What is the y you have to put in? Y squared. Can I put y cubed or not? Cannot, right? Because right hand side there's no cube. Okay. If you differentiate, if you see, if you have y here, you put y cube, then y cube will have to go to 0 in the end. Can you put x or not? You can put x, but what happens if you put x? You only have x. Here got 1, here got 0. X squared, how to find x squared? No x squared, you can never equal, okay? So you need to find at least as big as the gx, okay? So we put x squared. So we put a general second order polynomial a x squared plus bx plus c. So we want to try and find a, b, c now, okay? So this is the method of undetermined coefficient. So ABC is the undetermined. Okay, so we try to solve for ABC. Okay, so we try and guess. We guess that this is the form we want, and then we want to find what is A, B, and C. Okay, can make sense or not? Okay, so we want this to solve our equation. So meaning I need to sub the derivative into my equation. So y prime prime is 2a, okay, plus y prime 2ax plus b, and then minus 2y, so minus 2 times ax squared minus 2, so minus bx, so plus bx plus c equals to x squared. Okay, I think there's one question looks like what Homing asked. Why I put plus here, don't I put minus? Homing will ask this kind of question. I predict already. So why I put plus, why I don't put minus here? Because B and C is undetermined, right? So it can be absorbed into it. Okay. If it is minus, then B maybe minus later. We'll get a negative number. Okay. So this is a general rule of thumb. We will see more example later, and then we will make a summary. Okay, we'll see more example and then we try and make a summary. Okay, let's try this one first, x squared. Okay, so all together, what do I have? Minus 2a x squared plus 2a minus 2b x plus 2a plus b minus 2c equals to x squared. Okay, so meaning what? You will get 3 equations here. Okay, what are the 3 equations you will get? You compare the coefficient. Okay, so this means 2 minus 2a must be 1. Okay, and then 2a minus 2b have to disappear because there's no degree 1 term. And then the coefficient also have to disappear. Okay, so these are the 3 equations controlling 3 variables. Okay, so you can solve it. compare the left-hand side and the right-hand side. Okay, let me write down. So we need to compare left-hand side with right-hand side. Okay, compare left-hand side with right-hand side. Right-hand side, there's no degree one term and there's no constant. Okay. Okay. So A equals to minus half. Okay, B equals to what? A, which is also minus half. C equals to what? C equals to 3 over 2A, which is minus 3 over 4. Okay, so the particular solution is minus half x squared minus half x minus 3 over 4. So are we done yet? Why? We still need the solution to the homogeneous part. Okay, we still need to solve the homogeneous part. How to solve the homogeneous equation here? So what's the homogeneous equation here? Y prime prime plus y prime minus 2y equals to what? 0. Okay, so if you want to solve this, you need to change this into a characteristic equation. Okay, make into R. So you get R squared plus R minus 2 equal to 0. Okay, and then this is what? How many root? 2 real root R plus 2 times R minus 1. Okay, so you get R equals to minus 2, 1. Okay, so what's your general solution? C1 times e to the minus 2x plus C2 e to the power x. So all together, what do you get? Y equals to yp plus yc equals to yp is what? Minus half x squared minus half x minus 3 over 4 plus c1 e to the minus 2x plus c2 e to the power x. Okay? Yeah, so tomorrow we continue with surface integral and then finish this ODE and then we do summary and then give you exam tips and then we take a group photo and then bye-bye. Okay? Okay. Don't know. I don't know. Yeah.